So let's calculate the capacity of Hopfield module because we have a set of patterns. For example, we have P patterns and we have N neurons, N number of neurons. We want to see how much patterns can be stored and retrieved from this associated memory in your brain or in your artificial neural networks. Doesn't matter. So we have some input stimulus, and then suddenly your brain, after some time, after some steps in the dynamical system, is converged to these patterns, and we retrieve this. So we have memory collection, and then the connectivity is this multiplication of these patterns. And this is a dynamical system that we are working on. We want to know the fixed point of that. And we want to make sure that those fixed points are stable points. Otherwise, it never converges. So you know that a nonlinear dynamical system, either it converges to the limit cycle, if you are familiar with the nonlinear dynamical systems or nonlinear control and those things, or either it is periodic, or either it converges to a tractor, a stable point, and it is good that you become familiar with stable manifold theorem, unstable manifold theorem, center manifold in classical dynamical system, because those are local things. But in general, when you want to know the global dynamics, it passes through different, sometimes it goes to different equilibrium and then comes back, and it may have a chaotic behavior. But in Hopfield networks, we can analyze it very simple because the rule, you will see how we analyze the fixed points. And so it's like transformer architecture for me. Because if you mask something here, you don't know here, then you understand the rest of that. Your brain can understand the rest of that. This is for images. You can do it for text. You can do it for sounds, speech, any kind of modalities. So the associative memory and Hopfield networks are very interconnected. So sometimes you converge to this fixed point sometimes. So, for example, if you start from this initial condition with this pattern, then you converge it to this fixed point this is the real pattern. But this is something that suddenly it's like a noise. But for example, when I'm in the bathroom and look at the water on the ground, suddenly my brain sees something. For example, a phase or equation or something. So it converges, your mind converges that noise to something meaningful, depending on your perception, your culture, and different things. So energy and optimization problem, when we say energy in this context, that is equivalent to a Lyapunov function in the study of nonlinear dynamical systems. Because, for example, in nonlinear control, we always design a Lyapunov function such that the dynamics converges to the fixed point, or at least the energy is reduced so that it converges at least to a limit cycle. But when we want to change one of these, we want energy to be reduced. So we want to discover W. What is the weight? What weight should we design? And John Hopfield designed it in 1982 when I was just 2 years old. So, Sepp is a great professor, very good lecturer. And this is his slide. This is his beautiful slide. You see that there are n-binary patterns, and W is the weight matrix. So if you synchronously update it, it becomes this. But the brain uses asynchronous update. So we pick just one and update it. And convergence is reached if it doesn't change, if this dynamical system doesn't change. So it is called content memory because you are mapping from KISI to X. KISI is the patterns that you want to remember and store. And decoding is just reverse mapping of that. And so it's a general kinds of Hebbian learning because it's not just one pattern. We have m number of patterns. So I call it a generalized Hebbian learning. And you see this symmetric weight W, because this makes it symmetric, it has good properties for the convergence of that dynamical system. So again, sometimes it reaches some spurious fixed points that are not good, because just a little noise can go to another minima. So these are spurious points. We don't like them. Like this is just a parasite, and we don't like it. What we are looking for is converging to these locations. Our patterns should be stored at these locations. And Daniel Amit, he's great. He's a great neuroscientist. I could only find 2 or 3 lectures of him on YouTube, unfortunately. But he is a great person, And I want to explain his original article in 1987 from Great University of Hebrew. And because the original approaches for the first approach to find the capacity of Hopfield networks was proved by Daniel Amit. That's why he's very important. And also, this article is very important after you read that. And I like this kind of articles because my mind is biased to our dynamical systems, because I started my career as an electrical engineering, nonlinear control, and those things. So that's why I'm fascinated by dynamical systems and chaos and Markov chains and those things. And Hopfield networks is great for those neuroscientists who want to use physics for biology. And you can see part of my informal article in medium.com that, so we have a dynamical system. I want to say the number of fixed points depend on the size of the network. And then I want to say that you can talk about stability of this dynamical system, but capacity, if you design this one, that is this is the weight that you are designing. And each one is d-dimensional. So it's the d-dimensional vector of 1, 1, minus 1. So it's d-dimensional, each x. Because the number of neurons is d, but n is the number of patterns. And the storage capacity, if you just like this you write this dynamical system, and I will explain it more in details. So we have the rest of that is just noise. You want to get rid of it. So if this becomes small, the magnitude is less than 1, then you get, and this forces the possibilities, the capacity that you can store in the dynamical system, that we should prove this one. So the memory is just limited by 0.14 number of neurons. And the neuron in this model takes binary. So this is a Hopfield network. This is the dynamic of that. We use sign activation function. In the original article, Hopfield uses that. And connection strength, we want to see that we want to set for the case that we have just one pattern, assume for simplicity. So this is if this satisfies, then we understand the dynamical system. So put W to be here. Assume that we have only one pattern. Then you will notice that, so this is a generalization of Hebbian rule, that we do it for p number of patterns instead of just one pattern. And in general, you can design different things. Not, for example, John Hopfield invented this law. You can invent a different law, and you have a different dynamical system. You have a different neural network. But let's talk about crosstalk term, which is very important. So if you just substitute, if you want to analyze the fixed points of this dynamical system, you just write it. And you just pick, these are mu, but our pattern, we fix a pattern nu, for example. And if you substitute this one, this W, inside here, it becomes this one. And just get this one out of the summation. I mean, you will notice that the rest of that you can consider it as noise, as I said in the previous slides. So if this becomes small, it converges. So because this term is important, we call it a new variable minus this one. So we call it that term because we want to analyze this formula. So what is important, if this term becomes greater than 1, so this one becomes greater than 2, and this one, so it makes neuron unstable. It never converges. So Kc is not equal to Kc, so it never converges. And then we can consider this term as some binomial distribution, but what we approximated by Gaussian distribution. We can because NP is large, and we know the variance of that, which is number of pattern divided the number of neurons of your neural network, and we can approximate. We do it in communication, in electrical engineering. We know, for example, what is noise. This is the error function. If you're familiar, this is error function. And now we can consider it as just a simple probability question. And if you work on that, you get those 0.18 number of neurons. So your patterns should not exceed this limit. Otherwise, it cannot store it appropriately, and it is mixed with other things. So it's a good approximation, this crosstalk term, which is that noise that I said, the higher order terms. And if you want to do it scientifically, we use Hamiltonian. We have in nonlinear control, we always have Hamiltonian dynamics. It's better than, because it automatically generates a good Lyapunov function. You don't need to worry, because H has a nature of energy, and you don't need to worry about designing a Lyapunov function for that. And then if you work on that, just like previous lectures, you will see that the energy is reduced. So we make sure that it converges. So if you substitute that, you make sure that it converges. So it must be pointed out that Kc are not the only attractors. So minus Kc is the reverse state, also called local, but not problematic as aforementioned. Kc is mixture state, are stable, different with any, but emerge as a linear combination of an odd number of memories. And for large P, there are attractors that are not correlated with any stored patterns. So when your number of patterns becomes large, it produces some spin glass states, which is annoying. And there are sources, one of the sources of spurious minima that I mentioned. So it would be ideal that they do not appear in the system, which is nearly impossible. But relatively small Bayesians for these are achievable. Because if the Bayesian of attraction is small, rather in comparison to this one, then it's not a big problem. And you can generalize Hopfield network for continuous decays. We call it modern Hopfield networks. And Krotov, I think, was the friend of John Hopfield, if I remember correctly, has worked on modern Hopfield networks. This is just a continuous version. And you see here, we have a different energy function. You add something differently. And the outputs of the neurons are real numbers because it's continuous. It's not just -1 and +1 anymore. The application of that is that you can use it for traveling salesman problem, or 8 rooks problem, or 8 in chess we have 8 rooks and 8 elephants. Not elephants, queens. 8 queens and 8 rooks. So you can solve this by designing a good potential, the good Lyapunov function. But there are issues with continuous Hopf field. Design the energy function for specific problems. For any problem, you should first check that if you can find a good Lyapunov function. And the variable of prob and neuron but continuous Hopf field is just one of the extension of Hopf field networks.